Hi everyone. In this video, I will be discussing about Module 2 of Semester 3 Engineering Mathematics, and that is applications of partial differential equations. The well-known partial differential equations are: first one is one-dimensional wave equation, that is dou square y by dou t square equal to c square into dou square y by dou x square. And the second one is one-dimensional heat equation, that is dou u by dou t equal to c square into dou square u by dou x square. Okay. First of all, we are moving to derive the one-dimensional wave equation, that is dou square y by dou t square equal to c square into dou square y by dou x square. Before deriving this one-dimensional wave equation, first of all consider the vibration of a structured string. Here we are deriving the wave equation. The figure is like this. Here we have a structured string with endpoints O and A. The string is of length small letter L. We are considering a portion from the string, that is P and Q. So we are deriving the one-dimensional wave equation by considering a small portion PQ. Here there are two tensions, that is forces T1 and T2 corresponding to P and Q. Considering a tightly structured elastic string of length L with endpoints fixed, that is O and A. Let the string be released from rest and allowed to vibrate. Here the problem is to find the deflection y of xt with respect to x and t, that is the point x and time. These are the assumptions for deriving this wave equation. The first assumption is the mass of the string per unit length is constant and the string is perfectly elastic, that is does not offer any resistance to bend. The third one is the tension in the string is so large so that the gravitational force will be negligibly small. And the fourth one is the displacement y and the slope dou y by dou x is small, so that the higher derivatives or higher powers can be neglected. So these are the basic assumptions required for deriving the wave equation. Here we are taking the one end of the string as origin O and other end as capital A, and we assuming the motion of the string take place in the xy plane. Consider a small portion PQ of the string where P is xy and Q is x plus delta x comma y plus delta y, and T1 and T2 be the tensions at the points P and Q, and alpha and beta are the angles made by tangents at P and Q with respect to the x-axis. Here we are considering the vibration of the string. Since the points of the strings move vertical, there is no motion in the horizontal direction. All the motions are in vertical direction. So the horizontal components of the tensions must be taken as constant. Next, we are moving to find the horizontal components of the tensions at T1 and T2. First of all, at T1, we have the figure like this. At T1 means the tension at P. So that is P, the tension T1, and its corresponding horizontal path is HP. Then joining the horizontal path with the tension, we get a right angled triangle. we want to find what is HP. For that, take cos alpha. Cosine is equal to adjacent side divided by hypotenuse, that is HP divided by T1. Therefore, HP equal to T1 cos alpha. So the horizontal component at P is T1 cos alpha. Similarly, we can find the horizontal component at Q. That is HQ is equal to T2 cos beta. Also, we can find the vertical components at P and Q. That is the vertical component. For getting the vertical component, we take the angle as sine alpha. Similarly, we can find the vertical components as T1 sine alpha and T2 sine beta. So these are the horizontal components and vertical components at P and Q. Therefore, the coordinate at the point P will be T1 cos alpha, comma T1 sine alpha, and at the point Q is T2 cos beta, comma T2 sine beta. All the vibrations are in the vertical motion. So we are taking the horizontal components as a constant. That means T1 cos alpha is equal to T2 cos beta is equal to a constant T. Therefore, the force, that is the vertical component of the force to the element PQ, will be difference between the vertical components, that is T2 sine beta minus T1 sine alpha. Okay, next we are taking m as the mass of the string and the acceleration of the element in the y direction is dou square y by dou t square. We have acceleration is velocity by time. So this will be dou square y by dou t square. Now, by the second law of motion of Newton's, it's stated as F is equal to mass into acceleration. So here the force is T2 sine beta minus T1 sine alpha. Okay, therefore T2 sine beta minus T1 sine alpha is equal to mass into acceleration. Here mass is m into delta x and the acceleration is dou square y by dou t square. Equation number 1. Next we are going to divide this equation 1 by the horizontal components. Okay, that is by T1 cos alpha, T2 cos beta and T. So we get T2 sine beta divided by T2 cos beta minus T1 sine alpha by T1 cos alpha equal to m delta x by T into dou square y by dou t square. From the first fraction, T2 will be cancelled, then sine by cos is tan. So tan beta minus tan alpha equal to m delta x by T into dou square y by dou t square. What is tan alpha and tan beta? They are the slopes at the point P and Q. Okay, what is the slope? That is the first derivative. So tan alpha is dou y by dou x at the point P and tan beta will be dou y by dou x at the point Q. So our second equation will be rewritten as dou y by dou x at Q minus dou y by dou x at P equal to m delta x by T into dou square y by dou t square. Rearranging this equation, we have dou square y by dou t square equal to T by m into dou y by dou x at Q minus dou y by dou x at P divided by delta x. Next we are taking the limit delta x tending to 0. Then this equation will be dou square y by dou t square equal to T by m into, what is limit delta x tends to 0? Dou y by dou x q minus dou y by dou x at point P divided by delta x is dou square y by dou x square. That is second derivative with respect to x. Taking this T by m as a constant, that is c square. Taking T by m as c square, our equation will be dou square by dou t square equal to c square into dou square y divided by dou x square, which is the one-dimensional wave equation. So this is the derivation of one-dimensional wave equation.